Mineral compositions is going to be our main heading today. In the textbook, this is on pages 90 to 108, although in this first 15-minute little lecture, we're going to spend most of our time in the 90s, pages of the 90s. Mineral compositions is a huge deal for a mineralogy course, no matter where you're studying, because it introduces us to this like basic nomenclature that allows all of us geoscientists to communicate one another about the different processes that we care about. Ultimately, we're building towards mineral formulas. And mineral formulas is probably, I don't know, it's one of the big two things you need to get out of a mineralogy class. So you can hear things like FeS2 or CaCO3 and immediately know that we're talking about a certain type of crystal structure or geologic environment or process. And in FeS2, really knowing the chemical formula is just as important as knowing a mineral name like pyrite, or CaCO3 is calcite, right? So this is where we're headed. You'd also know that we're headed towards, this is also can be have the exact same chemical formula, right? Aragonite has that chemical formula, and marcasite has this chemical formula. Right? There's all this embedded information in mineral formulas. The building blocks for mineral formulas are our elements. Our elements are summarized in the periodic table. There's been 118 identified by physicists over the last 100 years or so, but not all of these occur in nature. In fact, what are the numbers we have? The Earth is really mostly made up of only 15 of these elements. Most of them occur in really, really small abundances. There's only, of the 118, how many are actually found in nature? 94 of these are only found in nature, which means a bunch of them are actually just synthetic things that have been made in particle accelerators and high-end physics devices like that. So the major building blocks of the Earth, the major element, are called major elements. So Roman numeral 1 here is going to be called major elements. We're going to also talk about minor elements and trace elements later. But the major elements are our major building blocks. They occur at the weight percent level in the Earth. When I say weight percent, so 1 weight percent equals 1 over 100, all right? So 1 part for every 100 parts is this material. So an example of something that could be occurring at the weight percent, you may be communicating with someone in a rock or a mineral has a lot of silicon. You could say that there is 75 weight percent silicon in this mineral. That would be just a way to talk about things at the major element content. In the end, 99% of the Earth's crust is composed of 8 major elements. And I want you to learn these in order. So let's say this, 99% of crust is composed of 8 elements. Later in your career, you're going to probably learn about what the mantle is composed of and what the core is composed of. But for here, let's just talk about the crust. And the most abundant, I want you to learn this in order as well. The most abundant element in the Earth's crust is oxygen. By like far and away, it's the most common major element in the Earth's crust. Next is silicon, then aluminum, then iron, calcium, sodium, potassium, and magnesium. Most of the time, when we report these elements, right, and I do, learn that in order, it's important. These are most commonly, we're going to say this, most commonly reported as oxides. Sometimes they're called major oxides. And what an oxide is where you take a cation and you bond it to an oxygen. So, for example, and there has to be charge balance. So example, silica is almost always reported in geology as SiO2. Aluminum is reported as Al2O3. Iron is reported as FeO or Fe2O3. Just different ways to handle the iron 2+ or 3+ that can occur. Calcium is reported as CaO. Sodium, oh, that's nitrogen I put up there. We better fix that. Sodium is a +1, so it is sodium 2 oxygen, right? Because oxygen is a 2 minus. The charge of each of these actually does matter. Al 3 plus, Fe 2 plus, or 3 plus. Calcium is 2 plus, sodium is 1 plus, potassium is 1 plus, magnesium is 2 plus. So then we also have K2O, and then lastly MgO. Those are the major oxides. Now the minor, if we have a little bit less than 1 weight percent of something, well, we call that a minor element. Minor element. And the minor elements, these occurs at 0.1 to 1 weight percent in a rock, in a mineral, or in the Earth's crust. It's going to vary significantly in the mineral or the geologic environment, but like, let's just say in igneous rocks, titanium, or often reported as titanium oxide, this occurs at the minor amounts. So maybe it occurs at like 0.8 weight percent. This is just an example, okay? This is an example. Titanium occurs at 0.81 weight percent in, let's say andesite, right? It's just some igneous rock. So it's not above 1 weight percent. It's not a major oxide, but it's there in some kind of measurable and significant amount. Minor elements don't get much press. Major elements get a lot of press, and trace elements get a lot of press. So let's spend a little more time talking about trace elements. Trace elements occur at the ppm level. Occur at ppm level. Maybe 1 ppm, 1,000 ppm, 100 ppm. And when I say ppm, I'm talking about parts per million. So 1 ppm means 1 part for every million parts of the entire mineral or rock. So that stands, if you need to write it down, go for it. Parts per million. Sometimes with trace elements, we'll even talk about ppb or ppt. I did that bad. pp, they're little t's. Little p's and little t's. What's this one? Parts per billion, parts per trillion. So parts per billion, 1. And we actually do have the analytical capabilities in geoscience today to measure things sometimes at the ppb or ppt level. But most of the time with trace elements, we're thinking about things at the ppm level. So trace elements are very rare. So we do want to write that down. These are very rare elements, but they can be really significant or important scientifically or economically. But geologically, across the whole crust or planet, they're exceptionally rare. So let's say very rare elements, but important geologically or economically. There's so many different examples we could talk about here. When they do become, when they're dispersed, so sometimes they're dispersed at very low levels. An example of a dispersed trace element that we care about could be, how about uranium in zircon? Well, we can use the amount of uranium in zircon that radioactively decays to lead as a geochronometer. That means we can use it as a clock in a rock, and we can figure out how old the rock was. It's only occurring at the ppm level, but because we have sophisticated mass spectrometers that can analyze it, it is valuable to us scientifically. Now, economically, they tend to need to be concentrated by some geologic process. So let's say other times they are concentrated by a geologic process. And we'll do an example for this. When they're concentrated by a geologic process, commonly into like an unusual mineral, right? Like a rare gemstone, for example. But our example, let's talk about gold. So in the Earth's crust, if you average all the gold in all the Earth's crust, it actually occurs at 0.0011 ppm, an incredibly low amount across the Earth's crust. But we prospect for it when it and we mine it when it has been concentrated by some unusual process, volcanic activity or hydrothermal activity in particular. So this will get concentrated to economically valuable material, and we call that an ore deposit probably. So concentrated to economically valuable levels. Throw in a picture just for, oh yeah, to make you covet finding this rock and adding it to your mineral collection. So here is a vein of gold formed in a hydrothermal deposit that is very valuable. Well, how valuable does it actually have to be? This is just for fun, not on any exam or anything. But what I found out is that in today's economy, you have to have 5 grams per ton in order for it to be viable. It's not a rich deposit, but at least it's economically viable. Well, how much does that mean in terms of its ppm? Well, what ends up being is that there is 1 million grams in every ton. So if we have 5 grams divided by 1 million grams, then that gives us a concentration of 5 ppm. Trace amounts of gold can be very valuable. So I wanted to just do one more type of conversion. This doesn't even have a heading, but what is the conversion? What is the conversion for ppm to weight percent? This is an important question because you need to be able to do this kind of math in your head, and it ends up being not too hard. So a ppm we've already established is 1 over 1 million, right? And a weight percent is 1 over 100. So to make the conversion, we just need to make this denominator 1 million, and then we'll see some number over a million and some number over a million. So to do this, okay, let's do it like this. So we have 1 over 100. But now we need to add zeros to the numerator and the denominator to get it over a million. So if we add one number, we have to add 1 here. So 1 weight percent is equal to 10 over 1,000, or 100 over 10,000. And the real answer is 10,000 over a million. 10,000 over a million is equal to 1 weight percent. So which is equal to 10,000 ppm. That's a conversion I'd like you to be able to do in this class and in any future class you may have with me. So the last thing for our notes today is just kind of a concept that's important in mineralogy and in mineral compositions, and that is how variability in a mineral composition can be handled. So variability in mineral composition. Things that are permitted by nature and actually that we see, because minerals are very rarely pure and they have substitutions in their crystal lattice at the major, minor, or even trace levels. And the way we refer to this variability is called solid solution. Solid solution. Oh, glitching out a little bit here on the pad. Okay, so solid solution. At the simplest, this means mixture. Like a chemical mixture. But I don't want you to put that on any exam. Okay, instead I want you to put a more formal definition for solid solution, although if you think about it as a chemical mixture right off the bat, you're at least starting from a good place. Here's the definition. It's a possible range in mineral composition because specific sites in a crystal structure can be occupied by 2 or more ions. That was a lot of words. We're going to write them down together. It's a possible range in mineral composition because specific sites in the crystal structure can be occupied by 2 or more ions. When I say ions, most of the time this is the cations. And we'll just do an example where there is solid solution between two cations in a mineral group called the feldspars. There is a feldspar called albite that has a chemical formula of NaAlSi3O8, and it has a complete solid solution to another mineral called sanidine, which has KAlSi3O8. Man, my writing pad's glitching out a little bit here, team. Our solid solution is between sodium and potassium, going between these two minerals of albite and sanidine. You can have 100% N-member potassium, you can have 100% N-member sodium, and you can have any number between. You can have 50-50, 70-80, or not 70-80. The math has to add up to 100, doesn't it? 70-30, or even 30-70. It doesn't matter. It's complete solid solution between the two. There are rules that can allow for solid solution or block solid solution. And here's the rules that we have. So we're going to say rules for solid solution. There's 3 of them. Number 1, there has to be availability. You cannot have solid solution between potassium and sodium if you don't have either one or the other. So you have to have the cation available. That's probably why, I don't need to talk about it anymore because it's more obvious. But even if everything is available, you do have to have size that fits. You have right into the crystal lattice spots, and what ends up happening is you have to be plus or minus 15% radii similarity between the two cations. So here's a image showing the size of different atomic radii, and I said before that we can do an exchange between sodium and potassium. The charge, oh boy, that's what we're getting to next, okay? Charge is where we're headed next. The charge on both of them is 1+. So we're going to satisfy charge balance, but in terms of size balance, look at that. Potassium is quite a bit bigger than sodium. It might be right on the cusp of being too big, but then take a look at these two. Look at potassium and calcium. Sorry, not potassium, what is that? That's sodium and calcium. The size of those spheres are almost identical the same. There can be fantastic solid solution between sodium and calcium. The one problem with that one is that you have to maintain a charge balance. So we're going to say here, we're going to say charge balance, this is the 3rd rule, must be maintained. And there's 3 ways that you can do this. One is if there's the charge of the cations is the same. So let's say same cation charge. And our example for that one we've already done. That one is potassium plus exchanges for sodium plus. There's not going to be any problem in charge balance because they're both just 1+. But what about sodium and calcium? Well, in that case, one's a 2+ and one's a 3+. And so for that, we have to have something called coupled substitution to maintain our charge. So this requires 2 or more. So here's the example we'll do. Example, NaAlSi3O8, that's albite. It will have a complete solid solution with anorthite, which is CaAl2Si2O8. There are 2 things being exchanged here. We have sodium 1+ being exchanged for calcium 2+. But at the same time, to maintain charge balance, there needs to also be more exchange. And the other exchange is that silica 4+ is being exchanged with aluminum 3+. So that when this solid solution occurs, right, we have a change of 5+ being exchanged with 5+, right? Because 1 + 4 is 5, 2 + 3 is 5. And if we have this coupled substitution happening, then this solid solution is allowed to occur. And then the last example, this one's kind of pretty, so let me throw in pictures I'll do pictures after. We'll do pictures right here. Okay, so here's our example. We have a mineral called microcline. It is pink, and we have a mineral called amazonite, and it is this stunning blue color. How does this work? Well, there's a solid solution that's allowing it. And in this, let's say, we'll just write down the process here. Vacancies are produced. My notes are getting a little messy here. So here's going to be our example. We have microcline, which is K-A-L-S-I. Come on. All right, sorry, my computer's glitching out on me a little bit. I'll start over. This is K-A-L-S-I 308. And microcline has a microcline. And this as a solid solution with amazonite, and the chemical formula for amazonite is KAlSi 308. Oh, those look identical, right? Except for there's trace amounts of Pb2+ that sneak in for just a couple of the potassiums. When you have that Pb2+ exchanging for a K1+, then the thing that has to get left behind is the lead will create a vacancy. I'll just put it like as a dotted line with a V on the inside, and that has to be exchanged with another K+. So that over here we have 2+, and over here we have 2+. So amazonite has this stunning bluish green color because of trace Pb2+ and vacancies.